Hi guys, today we're going to be talking about work and power. So we're going to be reviewing work, since we talked about it last time. We're going to talk about what is power, how do we define that in physics, and we're going to talk about how do we calculate power. And we're also going to talk about some of the graphs that we'll see this unit. We're going to talk about force versus distance graphs and work versus time graphs. Let's get started. So the physics definition of work is that it's a transfer of energy. And we have two requirements for work. We have to have a force that actually causes an object to move, and that force has to be at least somewhat in the direction of the motion. So for this first one, a force causes an object to move somewhere. Remember, we had an example of just holding a book or pushing against a school building. If you're pushing against the school building all day long, sincerely trying to get it to move, you might get really tired, but you haven't done any work because you haven't actually succeeded in moving anything. And the other example we gave was for this second one. If we think about a waiter carrying a tray of food, the waiter's moving forward, but the force on the tray is upward, so there is no work done by the waiter himself. If you want to get technical, you can say there was some work done by friction, since the tray of food does not slip off of his hand, but the waiter himself has not done any work according to physics. And then we have our equations: work equals force times distance, when all of the force is parallel to the motion, and parallel just means the same direction. And then if we have an angle, we have work equals F cosine theta d, or sometimes it's also written as FD times cosine theta. Remember, in math, it doesn't matter where what order you multiply your variables in, so long as you make sure to close your parentheses on that side of the angle, you'll have the same answer. Also, since we're dealing with angles, make sure your calculator is in degree mode, not radian mode. And remember, our unit for work is joules. So let's take a look at this graph. Graphs in physics are super powerful. We can tell so much information from them. And they come up all the time. So if we have force times distance equals work, and if we have force on one side and distance on the other side, that means any graph of those two in the middle, in this shaded area here, we can find the work. So work is the area underneath the curve. And underneath can sometimes be a misnomer, because what if we have negative force? So we have force over here, 0 in the middle, distance over here, positive, negative. What if our graph line, I'll draw it in a different color, what if our graph line goes below the x-axis, below the distance, and then over? In that case, we need to find the area between the graph line and the x-axis. And since this force is negative, this section here will have negative work. And last time we said work and energy were not vectors. So why is there a negative here? Is that a correct thing or is it an incorrect thing? work can be negative, but it's still not a vector. So when it's a vector, it tells us a direction, up, down, left, right, north, south, east, west, right? In this case, positive work means we added energy, and negative work means we removed energy. So it's kind of like in and out, so they're kind of like directions, but not really. Not in the same sense of left, right, up, down. So for this, just to summarize what we've seen on this slide, if we have a force versus distance graph, and it asks you to find the work, find the area of whatever the shape is on that graph. This graph here is a triangle, so find the area of a triangle, which is 1/2 the base times the height. Over here we have a triangle here, and then another triangle here, and a rectangle of sorts, and depending on the graph, it might ask you to find it somewhere else. Find the work it took to move it from here to here, and then you would only need to find this triangle, the first triangle. Or it could say find the work needed to move the object from 0 distance to this distance here, and then you would have to find the area of both of those triangles. And remember, the one, once it goes underneath the x-axis, it will be negative. Now this graph looks familiar, but it's not the same graph. Notice, this axis is different. Remember, previous units, we saw force equals force times time. Force times a change in time, or a unit of time, is impulse. So this graph does not give us work, even though it looks exactly like the other graph. This graph is force times distance, so it's work. And this graph is force times time, which is impulse, or change in momentum. So be careful when you see graphs. If you get confused, go back to your equation sheet, if you have one, and see what equation matches with your axes. If you have force and distance, look for an equation that has force and distance in it. If you have force and time, look for an equation with force and time in it. And power. So power is the rate at which work is done. And work, our definition for work, remember, was energy transferred. So power can also be stated as the rate at which energy is transferred. But if we really want to simplify it, it's how fast energy is being used. And hint for anyone going into pre-cal, a rate is something divided by time. So in pre-cal, some popular questions for teachers to give would be, what is the rate at which water is leaving a leaky bucket? So in that case, it would be the amount of water divided by time. In physics, we've already seen 2 rates. We've already seen some things divided by time. What 2 things were those? One of them was the change in position over time, which was velocity. or we can say it as the distance divided by time, which was speed. Right? So velocity and speed are related. One is a scalar, one is a vector, but they're both very similar quantities. The other one was acceleration, which is the change in velocity divided by time. So power, by our definition, is the amount of work we do divided by time, or the amount of energy we use divided by time. Now we've got some other equations, so let's see how we get those. Work is also force times distance, so we can also write the equation for power as force times distance divided by time. And since distance divided by time is velocity, we can also write it as force times velocity. Now, notice this is a capital P for power. This is not lowercase p. Lowercase p, remember, was for momentum. Capital P is for power. And its unit is represented by a capital W, which is a watt. And this unit, even though it's slightly obscure, you've heard it before, right? For the amount of energy that a light bulb uses every second, right? We have 60 watt light bulbs or 40 watt light bulbs or sometimes some other variations, right? So we can also think of it as joules per second, which is the amount of energy used every second. And in our other outside lives, we can also think of it as horsepower, but that's primarily used for cars and engines, and we don't use that in physics. Now, one thing, and this is mostly just extra information, one thing that's a little interesting is watts are not actually good for measuring brightness. They're good for measuring energy efficiency because they measure how much energy a light bulb uses every second, but it's not a unit for brightness. What is a unit for brightness is called a lumen, and that's kind of a newish unit. It was proposed in 1948, I believe, so it's quite new in the span of the sciences. And it's starting to gain popularity on the packaging. So now most light bulbs have the wattage, and this is a package for an LED light bulb, and they are very efficient. They only use 7 watts, which is 7 joules of energy every second, as opposed to older light bulbs, which used 40 joules of energy every second, or 60 joules of energy every second. Now notice, this light bulb has 470 lumens of light, so that's how bright it is, which is about the same as the previous, 40-watt tungsten light bulb. So a tungsten light bulb is the one that had the glowing piece of metal in it. It's not the fluorescent light bulbs that have the gas in it. They're tube-like. This is the kind that had the little squiggly bit of metal in it. So it's the same as a 40-watt tungsten light bulb. And the last thing I want to show you is this over here. This little symbol says, "Please don't put me in a trash can." And it's become more and more and more common, and it's just something to be aware of. If you see that on one of your items, especially cell phones, graphing calculators have this, Even the disposable batteries, like the Energizer batteries, have this on them. It says, please take me somewhere that will dispose of me properly. Don't chuck me in the trash can. Find somewhere else for me to go. Right? Because they can do bad things to the environment if there's too many of them. Just be aware. Now, there are graphs that are associated with power. We can have a work versus time graph. And since in our equation for power, work and time are divided by each other, so work is divided by time, that means instead of finding the area, we need to find the slope of that graph, and that will find us power. So that's another thing. When we had when we had force and distance, we were finding the area because our equation was force times distance equals work. When we were trying to figure out what work is, if we're trying to figure out what power is from this graph, we need to divide, which means really we need to find the slope. Because if we have work divided by time on this graph, we're dividing the y-axis from the x-axis. So we're finding the slope. When in doubt, go back to your equations, check and see what your equations are doing. If your equations are multiplied, you're probably going to need to find the area. If your equations are divided, you probably need to find the slope. And that's it for this time. So these are our equations for work. These are our 3 equations for power. Also remember that work can be the change in energy. So sometimes you don't need to go through this. You might need to find the change in energy. Also remember another equation that you might need is the weight of an object. The force of gravity equals mass times the acceleration caused by gravity. Because when you lift something, you are opposing the force of gravity, and you need to just be exactly counter to the force of gravity in order to do that work. So that's another force to remember while you're doing your problems. And remember, our unit for energy is joules, the unit for work is joules, the unit for power is watts. Be careful not to get these 2 things mixed up. And the unit for force is newtons. And these, all 3 of these units are combined units. They all, in order for our equations to work out, everything needs to be in meters. Not centimeters, not inches. Everything needs to be in seconds. Not minutes, not hours, not days. And everything needs to be in kilograms. Not grams, not pounds. If you have something that is not in those units, you need to convert it into something else. All right, I will see you in class for the examples. If you can't see me in class, then make sure you watch some of the other videos that have examples in them. See you soon.